Also talking about functions, this is skill 5 on page 6. We want to talk about odd functions and even functions. The definition of an odd function, the algebraic definition, is that when you input a negative x value, your output also becomes an opposite. So an opposite input also creates an opposite output. Or all signs compared to the original are opposite. What this means is that the graph, if you were to have a piece that ran up like this, and you were to have some point, x comma y, to input the negative x value over here, because here's the positive x, here's the negative x, instead of landing at the positive y, you're going to end up down at the negative y. So your graph will do this one. Negative x comma negative y. So we say that an odd function is symmetric about the origin. And as a good reminder for ourselves, we can say that it'll be negative x comma y, excuse me, negative y, x comma y becomes negative x comma negative y. It creates the opposite when you input the opposite. For an even function, when you put in the opposite x value, nothing happens to the output. It remains the same. If you plug in a negative x value, you receive the same y value. So again, if we were to do our graph, we were going to have a piece going up here. Here's your positive x, positive y. And you're going to say, okay, I'm going to change from a positive x to a negative x. You're still going to have a positive y coming out. So the graph would remain going upwards. Positive x, y. Change the x, you still have a positive y. This one we say is symmetric about the y-axis. Again, notice that we're using part of your rule of 4 here. Our algebraic or analytical definitions are the f of x's that you see. We have our geometric or our graphical, and then we have our verbal down here. So we're using 3 out of your 4. So what happens when you have something that is symmetric to the x-axis? Odd, we said, is symmetrical about the origin, meaning that if you were to rotate this about the point of the origin, it would land on itself. Even, if you were to reflect this across, it would still land on itself. But what about the x-axis? So you have something like this. If you were to reflect that across, you can have that as a picture. It's a type of symmetry, but now it's no longer a function. It does not pass the vertical line test. So we want to use these definitions to help us determine whether functions are even, odd, or perhaps neither, in which case you would have perhaps something that's not even a function. Well, this one tells us these are all functions. This one wouldn't. Or you can have something that perhaps is just a line. Or something that is over on the side and not symmetric about any sort of origin. Solve algebraically, then justify it graphically. So we want to use our first definition here. With f of x equals 3, again, try to input an opposite sign. So, algebraically, we can say, okay, f input the opposite of x, but the output is still 3. So there's no change to the function. It's the same output, so we say it's an even function. This one, where we input the opposite of x, now we're going to have the opposite of x squared plus 4. A negative x squared is still a positive x squared plus 4, so it's the exact same output. It's still an even function. Then if we have f of x and we input the opposite of x, we'll have 2 times negative x cubed minus 4 negative x. When we simplify, a negative x cubed is going to be a negative x cubed, so negative 2x cubed, negative times a negative plus 4x. This one gives us the opposite compared to our original. When all things are opposite, we say this is an odd function. Those are your algebraic justifications. When we do graphically, we can look at the pictures for this, and I'm just going to use a calculator for us. This one here, we have a straight line going across, so we'll say this one reflects about the y-axis, even. X squared plus 4. This one we're going to have your parabola, and looking at parabola, we say again, symmetric about the y-axis, an even function. And then lastly, we have our swoosh shape going through here. We're going through the origin, this side symmetrical to this side, opposite it, and then these little curves here. Again, if you were to put a pen and if you were to think about rotating it about, you're going to land in the same positions. So it's an odd function. Our last thought with this idea of odds and evens is, can you have something that's both odd and even at the same time? Thinking about algebraically, if you were to have any function and you put in the opposite, you're going to have one of two things. Like we saw up top here, you're either going to have the outcome be exactly the same, or it's going to be the opposite. You can't have an in-between. So because you can't have the in-between, we're going to say no, you can't have that. Also, you want to ask yourself about it graphically. If you have a picture and you're looking at some function, if I have a piece here, can I have a piece that lands even and then this can still reflect over it? No. Because then if I come this way, that's my odd, this is my even. I can't have both at the same time. It would fail my vertical line test, for one thing. So algebraically and geometrically you can't. So odds and evens, when you input an opposite, what happens to the outcome? What happens to the original?